Hey everybody. So today I am going to demonstrate for you very demonstrably that Transformers is a leaky architecture overall. And then so the very first thing is to define what exactly I mean by a leaky architecture. I'm going to ground this in two areas. The first is this research paper, SuperArc, a test for general and superintelligence based on first principles of recursion theory and algorithmic probability. A pretty dense paper, 71 pages overall, released on March 20th, 2025. But what this paper does is it breaks down very simplistically multiple tests regarding what we consider intelligence, or what we would call intelligence. And then within that, it makes a direct correlation between intelligence and compression. Everything I've been stating for a long time, essentially, that intelligence can be related towards entropy compression, and then you can utilize entropy compression to solve problems, and then you can utilize that in reverse to know whether or not you can solve a problem and how complex a problem is. P equals NP, right? And then so within that, the formula and kind of what breaks down within that is that what we find is that LLM models as a whole tend to struggle very strongly when it comes to like when we look at like these types of benchmarks here, very strongly when it comes to more complex problems, that they can't actually understand them as deeply. And then what they do here is they measure several instances and metrics within these models, right? And then this is the one that I want to pay attention to, this Shannon entropy, Shannon. Because what you can see here is that the Shannon entropy is increasing in these models, but it's increasing in a unique way. It's not increasing linearly like I would expect to in this instance. And then like none of these are actually increasing linearly when you look at them. They increase, right? Because what we were just looking at with this chart here is like if this weren't increasing, if none of these were increasing, there would be something very, very wrong here, right? Because that would be violating like thermodynamics and physics in every single way if none of these were increasing at all. But like what I would expect from a physics perspective is again a lot cleaner increase within these, like a lot smoother increase. So the fact that this increase isn't smooth, especially on the Shannon entropy, kind of like trips some like kind of like it makes me think about this, right? Like so that's curious that is what occurs there. And then we see within this that the models are showing like steep and sharp drops in accuracy compared to complexity. Essentially, they're not able to solve for P equals NP overall. And then like this gives us kind of a good grounding for these models in this architecture, right? Essentially, the grounding is that we have a long ways to go for overall generalizability, right? This is the ranking, like on their ranking system for ASI compared to where we're at now, and then they smooth it out. So it's 1.0 at the top of the scale, and then we're currently at 0.1, like as the tops. Anywhere between 0.1 and less than 0.1. So like 0.1 to like 0.01 or 0.001 perhaps is kind of the range and the stretch that we're there now. So like a long ways to go overall within that, right? And that kind of backs up my assumptions and what I've learned throughout all of this as well. Tying this to the second component, because I mentioned there's two, right? So the first is this research paper. Second is, let's look at the second law of thermodynamics itself. It's very straightforward, right? There exists a useful thermodynamic variable called entropy. A natural process that starts in one equilibrium state and ends in another will go in the direction that causes the entropy of the system plus the environment to increase for an irreversible process and to remain constant for a reversible process. Meaning very specifically that entropy should increase within a closed and or isolated system, right? And then it should increase a little bit differently depending on whether the system is closed or isolated. And then so that brings us to transformers. And then so that brings us to the only actual like question that I have within this philosophical question that is left for me to answer within this is whether or not a transformer model and like a AI model is a closed system or an isolated system. I think it's a closed system under the definition of thermodynamics, but it doesn't matter under either definition, because under either definition, so a closed system is a system that is closed and contained, but has external interactions. And then so in this instance, the external interactions would be environmental interactions that the model has. And then so environmental interactions would be an external interaction. And then to me, I think that anytime that you attach a sensor, then that is what allows for environmental interactions. And then so in this instance, these transformer models have sensors related towards pattern matching. And then so I think that that allows and physically allows for the process of allowing it to be classified as a closed system under physics. But under both definitions, again, entropy should always be increasing within that system, right? If we show and we look at instances where we're seeing a decrease of entropy in that system, that means that something is not fully closed or isolated within that system, right? And then if that weren't true, it would violate the second law of thermodynamics. And there's like absolutely nothing else that we've seen around AI that violates the second law of thermodynamics, right? Like making that crystal clear. If it's like AI systems follow this law just like every other system in existence, right? So if it is an isolated and or a closed system, entropy should always increase in the system unless there's like a flaw in that in isolated and or closed system, meaning that it's not fully isolated and or closed, and that there's what we would consider a leakage, an entropy leakage in this instance. Think of it like a helium balloon where you fill it with helium, but then air replaces, and over time helium leaks out of the balloon, right? And then because it's not a fully closed system, and nor is it an isolated system, and then so that would be the same thing with these with these transformer models with regards towards entropy. And I'm going to show that here to you very clearly and simplistically, right? So this Colab notebook explores the behavior of a simplified transformer model, focusing on the analysis of activation entropy and sparsity across its layers. I perform a bunch of experiments here, essentially 4 experiments, and I'll walk you through each and every one. And then the key concepts that you want to keep in mind are these. So number 1 is Shannon entropy. Shannon entropy measures the information complexity of activation of layer activations. Shannon entropy is the S within our second law of entropy equation that we're seeing here. Sparsity. Sparsity measures the percentage of zero activations, indicating how efficiently information is represented. So like in this instance, more sparsity or a bunch of sparsity would be bad, right? Because sparsity is just essentially setting all of the weights to 0. Like taking like a group of weights, let's say I have 5 weights, right? And the weights are 0, 1, 1, 0, 1. And then I just sparsity would be set them all to 0. All of a sudden, all 5 are 0, right? And that's so that's the definition of sparsity. Activation functions, nonlinearities that influence the flow of information in neural networks. Gradient norms, and we need to know less about, but they measure the magnitude of gradients during backpropagation, indicating learning progress. I'll show you why it's in experiment 3. And then transformer architecture is a neural network architecture that utilizes self-attention mechanisms. And then so with that, I think that there's that self-attention mechanism is part of this. That's my assumption up front within this. Is so with the self-attention mechanism, it acts like a credit card in an instance with regards towards prepaying for the compute that the model uses. But within that, it's not, there's interest to be paid overall, right? Like you don't get to just charge the credit card for free. And then so the interest that's paid in this instance is a leakage of entropy. Leakage of entropy, increase in sparsity is the 2 things that I will showcase in this throughout for you. So experiment number 1, what we do is I just build a simple transformer model. So as simple as I can, right? It's very simple model, 8 heads, 6 layers. And then I essentially track entropy throughout each one of the layers. And then that's all I'm doing is like from layer 1 to layer 2, 3, 4, 5, right? And then so if this is an isolated system, what would happen is that we would see increase in entropy across the layers, right? As the information passes through from layer 1 to layer 2. Layer 2 would have higher entropy than layer 1. Layer 3 would have higher entropy than layer 2, etc., right? And so that's what would happen if there's a completely isolated system with no entropy leakage. If we don't see that, within this, that means that entropy is leaking somewhere in that process between layer 1 and layer 2, or else it's violating the laws of thermodynamics. And then so what we go through here, we see very specifically decrease across the layers. Right? And measured here, right? And this is a very small, very sparse decrease, right? Like, I mean, we're talking about 9.8665 compared to a decrease down to 9.8625. But it's a decrease, and it's a measurable decrease. And I ran this like 4 different times. You can try it yourself. It will decrease every single time. Rather than increase, right? And so it's either violating the second law of thermodynamics, which nothing else in the universe does, or there's an entropy leak within the system between the layers. It's one of 2 possibilities, and like physics-wise, that's it, right? So that's experiment number 1. Experiment number 2, let's go ahead and I want to track this very specifically across all of the different layers during a training process, right? So I train the model in this instance. In this first instance, I'm just like giving it like random data and then have it pass and do whatever it wants on random data. And then it ends up in a very slight but still measurable entropy reduction, which again, entropy reduction shouldn't happen in this system, according to the second law of thermodynamics. So unless you have a leakage. And then we go through here, and then we're just measuring out again, right? Small, very slight and subtle, but there is leakage going on here. Like very specifically, again, like if you're following physics, there's a leakage going on here. Or this is the one unique system that we're watching an experiment that is unique to literally everything else in the universe. It's one of the 2 possibilities. I go with entropy leakage. And then so the next thing, and the next experiment that we'll go with here is I want to add ReLU with it, right? and then so interesting, because I was like, well, okay, this is, to me, like when I was testing, I was like, this is what I was expecting on some level, but this isn't accounting for the full leakage. I thought that there would be more in this system. And so I was like, where would be the next place that I would look for it? Within the activation function. Just very simplistically, like, I don't know, like, I guess just like my engineer brain, right? like as I'm thinking through this, I'm like, okay, where's the next place to go? Activation function. And then so I test that out, and I test with ReLU very specifically, and then boom goes the dynamite. We see a very stark jump in the decrease of entropy, right? So this is the decrease in entropy across different layers. And then so very specifically, and outlining this, ReLU is utilized and added on for and with the back propagation process, which is very, like, that's, I mean, one of the reasons why I focused on that. And like, I just thought it would be within there. Is like, so ReLU is what happens when you're back propagating across the model, right? And then like, so ReLU is the most popular way to do that. And then you introduce large amounts of measurable entropy loss within the system by doing that. Like it's very large, very measurable, right? And then so the next thing that I do within that is like, so ReLU is not the only activation function that you could use. You can use other activation functions. And then it's also important to mention that the sigmoid function is present like within even like multi-layer perceptrons, right? Like sigmoid function has been present since like 1969. and then ReLU is like the newest innovation, but it's definitively like a big part of transformers overall. And then these other ones are kind of just like some variations on ReLU, mostly like JLU and SELU. And then 10H is like different. 10H is unique, and then hard switch is like just another like a competing, like I think hard. I'm not 1,000,000% sure on hard switch overall, but so. The final layer, sparsity activation, what we can see here is that there's not only do we have that 6% increase in entropy leakage with ReLU very specifically, what we have is a dramatic, like literally almost a 70% increase in sparsity with ReLU. And then it's with ReLU very specifically that we see that sparsity, right? So with ReLU, we're seeing a 6% reduction in entropy and then a 70% increase in sparsity just from this ReLU process. And then I tested out here. You can see the metrics, and they're all coming out, right? And this is like ReLU is far like worse overall according to these metrics than anything else, period, right? Like there's some that are actually like interesting. So SeLU and TANH are following what you would see within normal laws of thermodynamic entropy, right? So no leakage. So like that is interesting to me, right? Like these are creating more of a closed system. They like, if the activation function is kind of like a seal, then TANH and SeLU are a better seal overall than other activation functions, and that's why they perform better overall. It's kind of like, that's kind of what this is like measuring out according to what we're looking at here, right? That's just the data. I'm just looking purely at the data, right? And then the last test that I do within this is like, okay, let me take this and let me like fully train out a model, and then I'm going to use ReLU and then one of those variations, right? So I choose GLU in this instance, GELU, and then run through. And then what we see very specifically is difference in behavior here, right? So we see a specific decrease in entropy here, and then in this second one, and then we also on this one across the board, we see what would be expected, which is increase in entropy across the board, right? Like, so if this system were not a leaky system, and we're assuming that it follows the second law of thermodynamics 100%, I would expect these numbers and this type of number across the entirety of the system, right? It goes from 10.74 up to 10.84 up to 10.86, meaning that entropy is increasing in the system over time, which makes sense because it's a closed and or isolated system following the second law of thermodynamics. So entropy is going to increase in the system, as opposed to with this one, we go 10.12, 10.11, 10.12, and then and 10.1280 down to 10.12794 on the last one. Like not following the laws of thermodynamics. So again, there's only two possibilities for that. Either it is the only thing in the universe that has an explainable reason for not following the laws, the second law of thermodynamics, or there's entropy leakage within this system. And then to me, it's very clear that there's entropy leakage within this system. We can see, and going back up to our test before, that ReLU very specifically introduces entropy leakage above anything else that we introduced to this system, right? And then what we saw is, so we've seen and proven out two things very specifically within this. One is that the transformer architecture in and of itself has some leakage between the layers that's just built into the model architecture when it comes to entropy. The second is that adding ReLU to that very specifically compounds on this entropy leakage within the models. And then, so what does this mean in like terms of real world? It means that you will never get 100% accuracy with a transformer model, which makes sense, right? Like, because that's known. And then, so it hasn't been known, like, why? Like, why exactly can you not get 100% accuracy with transformer models? But because they leak entropy. and kind of here's the bottom line within this, right? But the next step that you should be taking within that is that there are tons of model architectures in which I can get 100% accuracy on the model. Like, I can get very good accuracy with different architectures than transformers. Like, I can't highlight that to people enough. These problems don't have to persist within this. Like, they're easy to overcome, right? It's just a matter of being able to understand, isolate, and then now that we understand that this is the problem, we just move forward from there. It seems a very simplistic road to me, rather than like trying to just dump trillions of dollars into this system, which literally leaks entropy, meaning that your trillions of dollars aren't going to combat Shannon entropy and the second law of thermodynamics, and Sir Isaac Newton is going to poon you. Like, that's just, I mean, how it goes overall, and it doesn't matter who you are on the planet, nothing changes that overall. And then so within this, it's pretty straightforward to me that like if you think that this research paper is accurate and all of the research around this is accurate and all of the research coming out around this, and then this particular one is from every single college and you like Oxford, etc., from that exists in the UK, stating all of this, right? The King's Institute for Artificial Intelligence from King's College, etc., is all saying these same things, that it's all tied to intelligence, and it's all tied to entropy compression. And I'm showing you literally with undeniable proof that entropy compression is leaking within these particular systems. It should give you a very clear road that this isn't the way forward, right? Like, I can't break that down any clearer from a scientific perspective, that no amount of money, hopium, wishful thinking, etc., is going to change the equation that transformer architecture leaks entropy, and that entropy is directly related to intelligence. And so here it is for you overall. I'll leave a link to all of this. If you like this type of content, please like and subscribe. Thank you very much.